Now the second example here. You have to bear this time because I don't have the time to animate, because when I want to solve this problem, I have to do it fast. Yeah. Maybe if you, let's say, for example, you have any questions that you don't know, you can ask me. Yeah. Now, a 6-meter long hollow bar. Okay, a 6-meter long hollow bar. Okay, of circular section has 140 mm diameter for a length of 4 meter. Okay, so that means this. Okay, so I have drawn the diagram for you actually. 4 meter. Okay, while it has 120 mm diameter for a length of 2 meter here. Okay, the bore diameter, that means the hole, H-O-L-E, the bore diameter is 80 mm throughout. That means you have a hole throughout the entire rod. Okay, the composite bar or the composite rod here. So the hole go through straight away. Okay, so find the elongation of the bar. That means find the total elongation of the bar when it is subjected to an axial tensile force of 300 kilonewton. See, I've given you the force 300 kilonewton acting at the edges also again, acting at the outer edges. So what about the intermediate? Again is 0. Again is 0. So you can apply principle of superposition, or you can say that the force acting at the first part is equal to the forces acting at the second part, like that. But then it's safer to work out based on principle of superposition. So you just standardize your way of working. So if you are using principle of superposition, so it is readily, okay, shown in the diagram, the first diagram itself. You can split it into 2 parts like this, exactly 2 parts. Okay, the red and the purple. So you got AB and you have BC. Okay, so part 1 and part 2. So since this 300 kilonewton here is given, so straight away we just, okay, make it easier. Okay, to make it easier, we straight away pick up the force based on the outer edges here. Okay, so in this case, I pick up 300 kilonewton. So, and then I have to look into the equilibrium of this part here. Okay, so what I have to do at section B here is that I have to consider 300 kilonewton. This arrow here, see, must be opposite in direction to this. And it must be equal in magnitude, 300 also. So in order to make this section or this part here to be equilibrium, so 300, 300, okay, state of balance. Then the second part is the purple color part, that is section BC. So now when you look back into the original diagram, at section B here, you have 0 forces. So, but then when I consider the part AB, I have considered 300 here, but originally is 0 here. So therefore, to make the net force acting at section B here to be 0, therefore, the second time when I reconsider section B, for the second part, I must consider the 300 here acting towards the left, which is opposite to what you have here. Okay, so that when you take net, 300 minus 300 becomes 0 here. Okay, because originally it's 0. So for the equilibrium of part BC, or the second part, since I have considered 300 towards the left, then I must consider 300 towards the right. And then finishing by checking this 300 here, is it the same as the 300 given here at the section C? So in this case, it's the same. So you are safe to go. Okay. Then once you have found out the forces acting at each part, then you go for the cross-sectional area. So since this is hollow, so that is why you have pi over 4. You can use r squared minus r squared. You can use r squared minus r squared. You can use pi r squared, or you can use pi d squared over 4. So here in this case, I have used mm. So cross-sectional area is in mm squared in terms of pi. Why I don't multiply it with the pi? Because I don't want to deal with all those decimal places. Okay, then section BC. So you have section BC here. Again, put in the diameters. That is 120. This is 120, and the hole is, or the ball is 80. This one just now was 140 and 80. So this one is 120 and 80. So you will find out the cross-sectional area of this second part. So once you have found out the cross-sectional area, then you go for the total deformation by taking the total deformation as the sum of the deformation of each individual part, A, B, and BC. Now again, the P I have extract from, or the F. Sometimes I use F, sometimes I use P. It's the same. For forces, you can use P or F, okay, for the force or the load. So I have extract from the main formula because again, okay, the forces acting at both the parts, they are the same. So I can just straight away extract it. And then in this question here, okay, they have only given us one E value. One E value. That means both the parts here, they are having the same material. Same material. So you extract the E. So you can find out the total deformation of this bar. Okay, that's all for this second example.